Okay. Now let's, I'm going to share my screen. And so I'm going to go over this presentation now, which is the more theoretical stuff in a sense that has to do with the multivariate distributions and inference. I forgot the name of it. It's presentation AM02, multivariate distributions and inference. Okay. Well, let's talk about the multivariate distributions. Let's start with the discussion with the simplest case. That is when we have two variables. It's a bivariate random variable, random vector now. It's going to be a random vector. And let's suppose that those two variables are, for example, the height and weight of an individual. So as you can see, each observation will be an individual. And the two variables that we're measuring in the individual are height and weight. Okay. So that will be the case in general. This is the bivariate case. If we have three variables, we will have three measurements on each observation. If we have p variables, which is the p-variate case, we have p variables that are measured on n subjects or n observations. Okay. In the case of bivariate random variable, let's take this example with a person's height and weight. We can look at the height and weight individually, okay, and that's what we did in the statistical methods when we looked only at one variable, and we could try to estimate the mean weight and the mean height for the individuals and so on. We could try to estimate and make inferences about the mean height of individuals in a certain population. In the bivariate case, we assume, as this is the case, since these are measurements taken on the same individual, we cannot assume that these two are independent. Okay, we cannot assume that weight is independent of height, because both measurements are taken on the same individual. So there's a link between those two observations. So in the bivariate case, we start looking, for example, at the covariance between the two variables. Okay, how does one variable vary with respect to the other variable? And the covariance is defined as the expected value of the random variable x minus its mu, minus its mean, times random variable y minus its mean. And this is actually, if you develop this equation here, it's algebra. It's expected value of x times y minus the product of the means. That's the covariance between x and y. If two random variables in a bivariate vector, random vector, are added or multiplied, they are also random variables. And the expected value of the sum of these two random variables will be expected value of x, the first variable, plus expected value of y. And something that you learned in statistical mathematics statistics class is that the expected value of x times y will be the product of the expectations if x and y are independent. So if x and y are independent, the expected value of x times y is the product of the expectations, but that only happens when the two variables are independent. Now, covariance measures linear relationship. It doesn't measure independence, covariance. For example, if you look at this set of data, there's a clear relationship between x and y, okay? There's a quadratic relationship between x and y. However, the covariance will not show that quadratic relationship because covariance only measures linear relationship and not independence. These two are dependent. These y and x here are dependent. Let me Take a look at the chat. Okay. Presentaciones is AM02. I forgot. I think it's multivariate. There was a question in the chat, so I'm answering. Is AM02. And put the chat here again.
Thank you, teacher.
Okay. Okay. If X and Y are independent, then their covariance will be 0. If X and Y are independent, their covariance will be 0. But the fact that the covariance of two variables is 0 doesn't mean that they're independent. Okay? If they are, the covariance is 0. Now, if the covariance is 0, that doesn't imply that they are independent.
It's just a one-way implication.
Yeah, that's right. Except in one case. If X and Y have normal distributions, then covariance equal to 0 implies independence. But that's the only case, when both are normal distributions. Since we never know the population variance, nor the population covariance, nor the population mean, we use the sample covariance to estimate the covariance of two random variables based on a set on n observations of both variables. So the covariance will be the sum of the cross products of each variable minus its mean, its sample mean, divided by n minus 1. And that can be expressed as the sum of the x times y, the product of the random variables from I equals 1 to n, we have n observations, minus n times the product of the means, divided by n minus 1. Now, why do you think we divide by n minus 1 here? And not by n? Remember the argument when to estimate the variance of a random variable, one random variable. To estimate the variance, you take the sum of xi minus x bar squared divided by n minus 1. What was the argument to divide by n minus 1 and not by n? See, if I only had one random variable x, then we estimated sigma square as the sum of xi minus x bar squared divided by n minus 1. Anybody remembers why we divide by n minus 1 and not by n? We have n observations. Nobody recalls that. If we divide it by n minus 1, we make the estimate unbiased. Okay.
We made the estimate on what?
If we divide by n minus 1, then this estimate will be an unbiased estimate of sigma squared. So that the estimate is unbiased, that's why we divided by n minus 1. Because the MLE, the maximum likelihood estimator of sigma squared, is dividing by n. But by adjusting dividing by n minus 1, we make it an unbiased estimate. That's why. Well, the same thing happens here in the multivariate case. We're going to divide by, if we have n observations, so we divide by n minus 1, so that this sxy would be, well, so that s squared xy would be, if you want to use this notation to remember that it's the variance, would be an unbiased estimator. That's the sample covariance. And as in the, as we know, this the variance and therefore the sample covariance will be affected by the units of measurement. So that's why we standardized, and instead of looking at the covariance, we normally look at the correlation, okay? Because the correlation is bounded. We know that the correlation of two variables is always between -1 and 1. So we eliminate the effect of the different units that we may be considering, because imagine that your x's are in the tens, okay, in the tens in units of 10, they're around 15, 20, 30, etc. And your y's are in the order of a million, for example. Then that definitely is going to affect the size of the covariance, because the size will not say much. The size of the covariance of the magnitude of the covariance will not say much because they depend on the units of measurement. So to avoid that, that's why we focus on correlation, because correlation is the covariance divided by the product of the standard deviations of each of the variables. Okay, so that's that we standardize, and we know that rho will always be greater than or equal to -1 and less than or equal to 1. Okay. For those who already took a linear regression, if your points, if your data is very close to a straight line, then you'll see that the correlation will be very close to 1. If your data look like that, for example, here's x, here's y, and here rho will be very close to 1. Well, your rho estimate, your estimate of rho would be very close to 1. If instead of looking like that, they look like this. Oh, I lost my page here. If they look like this, oh, I'm doing something wrong with my iPad here. Let's see. If it was the blue ones, then for this one, the sample correlation will be very close to -1. So that's why we use the correlation, because it's bounded, and we eliminate the effect of the measurements, the scale of measurements of each of the variables. The sample correlation coefficient is the sample variance, the sample correlation divided by the standard deviations of x and y, by the product of the standard deviations. And this will also be between -1 and 1. Okay, -1 and 1. Now, the fact that we have correlation 0 doesn't imply independence. If we had a graph like this one that we have here, our correlation will be close to 0. Here, if you try to fit a straight line to this set of data, your correlation, your estimated correlation, will be very close to 0. And that doesn't mean that they are not related. There is no linear relationship, but because correlation, since it's based on covariance, only measures linear relationship, not other type of relationships. Okay. Here. And now I have to raise this thing, and I can erase it. I'm trying to erase them from here because I'm not being able to erase them from my iPad here. Clear drawings. Okay, this is a chart, for example. This is the data that we saw at the beginning. This is height in inches and weight. Okay, as you can see, there seems to be a linear relationship. It's close to a linear relationship between x and y. So we will expect a positive correlation, and it is in fact the sample correlation is 0.889. So the closer a correlation is to 1 in absolute value, the stronger the linear relationship between the two variables. The closer it is to 0, then the farther away from a linear relationship we have among the two variables. Again, sample correlation equals 0 does not imply independence. it only implies that there's no linear relationship. It would only imply independence in the case where both variables have normal distributions. This is an example where x and y are not correlated. Here, correlation will be close to zero. There's no clear linear relationship between x and y here. Now let's extend this thing to p variables. If we have p variables, then and we still have n observations of those p variables, and we'll call this observations y sub I one from 1 to n, and y sub I is a vector that has this is the ith observation for the first variable. So this will be the ith observation for the first variable. This will be the ith observation for the second variable, and this will be for the pth variable. So we have a p by 1 vector. Y is a p by 1 vector, and its mean will be the average of every one of the observations for the first variable, every one of the observations for the second variable, and every one of the observations for the pth variable, divided by n. Okay, so that'll be the sum of all the observations divided by n. That'll be the mean vector. So the mean vector is also a p by 1 vector. Okay, and has the mean vector has the usual properties. It is an unbiased estimator of the mean and so on.
Teacher, what do we define as p variable? Or
Pardon me?
what is the difference for a p variable?
A difference for a p variable.
Uh-huh.
These are different. These are y1, yi1, i2, and ip are the observations. This is the ith observation. I goes from 1 to n. We have n observations, and each of the variables is a different characteristic that we measure on the object, or on the. For example, if it's a person, one could be the height. The second one could be weight. Third one could be gender. The fourth one could be, for example, if he's married. Or the fourth one or fifth one would be the salary, and so on. So these are measurements that we take on a subject, whether that subject is a person or that subject is an image that we record some data from that image and so on.
Okay.
Okay.
Thank you.
And in general, that's what we'll be dealing with. As a standard, we'll use p for the dimension of the random vector, okay, of observations. And by default, we'll use n as the number of observations. So the way we write this thing down, since we have n observations, then we have a matrix that has p columns. So we'll use this. The p columns will be the p variables, and we'll have n rows, which represent the n observations. Okay, so it will be, for example, the first observation on the first variable, first observation on the second variable, and so on. In the first observation, the pth variable. And it will be the nth observation on the first variable, the nth observation on the second variable, and the nth observation on the pth variable. Okay. If you look at this notation, we're saying we wrote this thing as the vector y. Okay, this will be y1, y2, yn. Okay, and we're taking the transpose because we put this thing as a column vector. So if you look at by taking this transpose, we're taking this and make it a transpose. That will be yi transpose. That will be yi1i yi1 up to yip. Okay, so we're just transposing that vector. That's why I put it here as the transpose of those vectors. And that'll be the usual notation where we have each row is an observation and each column is a variable that is measured in that observation, okay? So the mean the sample mean estimate is just the average of this y1 through y2, yp bar, and so on. And we can express that as 1 over n times j transpose times y, where j is a vector of ones, okay? J is also, we'll also write it as a 1 with an n subindex. That means that it is a vector of ones. So when we take that vector, transpose it, that's why we have this transpose here, times y, that will give me the mean value for each of the p variables, okay? The mean from all the observations on the p variables. Now the expected value of y will be denoted by the vector mu, which is the mean of the first variable and the mean of the second variable up to the pth variable. So, and that'll be a vector also. That's a mu. We'll call it mu as the mean vector of all the p variables. Okay, and the sample mean has the property that its expected value is mu. Okay, so the sample mean is an unbiased estimator of the vector of means of mu. Then as we have the sample mean, we can compute also the sample covariance matrix. The complete name will be the variance covariance matrix. Sometimes I'll use it as variance covariance matrix, or just simply the covariance matrix. In the covariance matrix, what we have in the diagonal, these elements in the diagonal are the estimates of the variance. Okay, so S11 is the estimate of sigma 1 square of the first variance, of the variance of the first variable. S22 will be the estimate of the variance of the second variable, and SPP, the estimate of the variance of the pth variable. And the elements of the diagonal are estimating the covariance. So S21 will estimate the covariance between S21 is the estimate of the covariance between x1 and x2, which is the same as the covariance of x2 and x1, right? So this matrix here is a symmetric matrix. This matrix is symmetric. So the S21 is the same as S12. P1 is the same as S1P. It will be a symmetric matrix. And
normally you can see this as just a triangle matrix and it's okay, no? Just like the half of it.
yeah, but you see, a lot of the procedures depend on inverting this matrix. So you need to carry, I mean, you know it's symmetric. So in memory, in the computer, it's actually, they don't store the whole matrix. It's only the lower diagonal, the diagonal that are stored. But when you do operations, you need the full matrix.
Okay.
Okay. Here's the expressions for each of the SJJs, the estimates of the variance, and outside the diagonal are the estimates of the covariances of each pair of variables. Okay. Now the population covariance is will denote by sigma, and that's the covariance matrix of the vector y, of the matrix y, sorry, because we have n observations and p variables, And this will be the notation we'll use for the population covariance matrix. So instead of the S, which is for the sample, we'll use the sigma 11. So sigma 11, sigma 22, sigma pp are the variances of each of the p variables, and of the diagonal are the covariances between each pair of variables. And this is the expected value of y minus mu times y minus mu transpose. Okay, so this is a p by p matrix. See, remember y minus mu, this matrix here is a p by n matrix, and therefore y minus mu transpose is n by p. So the result of the product of these two matrices is a p by p matrix. See? Okay. So far, the only thing that's changing is that now, instead of considering only one variable, we're considering p variables. Everything else, the formulas are exactly extensions of what we saw in statistical methods, in mathematical statistics, or in the methods class. Okay. So as the same way we have our sample correlation matrix and our population correlation, our sample covariance matrix and our sample and our population covariance matrix, we do have our sample correlation and our population sample and population correlation matrices. We'll call R the matrix that has all the sample correlations. If you see this a matrix, that's also a diagonal matrix, but there's always one in the diagonal, because the correlation of a variable with itself is always going to be one. Okay, correlation of a variable with itself is always going to be one. In other words, when we compute the correlation of, if I compute the correlation, the sample correlation between x and x, at the same variable, what I get is sxx, which is the variance, divided by square root of sxx times the square root of sxx. So that's one. So the correlations in the diagonal are always one, and of the diagonal, the matrix is symmetric. Each of the sample correlations between the jth and the kth variable are the product of the correlation between the covariance between the jth and the kth variable divided by the square root of the variances, the jth variable and the kth variable, which we denote here by s sub j and s sub k. Okay. And the population correlation, we'll call that, this is a row, a capital row, but it looks like that. And that's, it'll just the same, one in the diagonal, it'll be symmetric. And these are the population correlations, which we never know, and we estimate by the sample correlations, okay? So far, so good, or are we okay so far?
Yeah, so far so good.
Okay. Now, this is an example that you're going to do. We have students in a high school come from different elementary schools. Their professor wants to determine if there are academic differences among the students from the three different high schools, A, B, and C. Now, to do this effect, they measure their academic performance according to the grades they obtained in their English and mathematics tests. You'll find the data in Brightspace. It's a file called eng_math_scores. It's an Excel file, and you don't have to carry the exploratory analysis of this data. Just exploratory, okay, with what you sort of things that you already know how to do in R, or if you want to use another package, that's fine. You can use whatever software. If you do it in R, let me one thing that you should know is how to read Excel files. My scripts. Scripts. Okay. This is this is a script. You're just going to do it. You don't need to all these packages here, but let me see if I put in Brightspace. So I have erased it from Brightspace, the head of the script. Look at the scripts. Unfortunately, it's there. I'm going to hide it because I want you to do it. I want you to do this exploratory analysis. Okay. Well, I will not hide it. You have this script there. Okay. So what I'm asking you to do is just follow that script. You're not going to reinvent the wheel. You can just follow that script to do the analysis. Now, to read Excel files, you need to load this library in this package. Read Excel, and install packages read XL. That you will need that to read an Excel file. Now, my suggestion is you set your working directory to wherever you have that file. Okay. So I'm going to see here, for example, where I am. Get WD. I'm already in the directory where I have the data. Okay. I'm already in that directory. If you are not in that directory, what you can do is in your lab, just look for where the file is, where the data file is. Let me go over here to the data. Status. And this is called English and Math Scores. English and Math Scores, okay? English and Math Scores. No, but this is not the file. It's English Math Scores XL. This is it. Go to Properties. I'll do it just in case. I'm to make sure that all of you can read the file. I'll go to Properties. I'll copy the route. And you do the same in your equipment, in your lab. And I'll say set working directory. I already have it there, but copy the route and replace every back shift diagonal, every back diagonal, just replace it by a straight diagonal only in this line. Okay. In datos, number occurrences. So once you do that, you will be in the directory where the file is, and you can just read the file. Okay. So did you find the script?
Yes, teacher, can you share with us the Excel file, please?
It's in Brightspace.
Okay,
It
thank you.
is, let me look for it. Let me tell you where it is. It's in the section that says data.
Data sets.
Data set. And let me open it. Data sets, and it's called English and Math Scores. Okay. In English and math scores. So the file is there.
Yes, thank
Read
you.
the file. Okay. And I'll split you guys into groups so that you can go over the script and share, load all the packages that you have there. It doesn't hurt to have them loaded. You will not need all of them here, but just do the exercise. And there'll be some commands there that you may not know what they do. Have any of you looked at the videos for the graphical analysis with R or not?
No,
Yes.
yes, teacher.
Okay, maybe do you want to do this thing here with you?
Yes,
Maybe divide you into groups,
Yes.
just to make sure that I'll explain every step what we're doing. Can you see my screen clearly? Can you see what I type in the window, in the script window? Or should I increase
Yes,
this?
teacher.
It's okay? Okay.
yes.
Well,
Teacher, I have a doubt.
yeah, let me. Yeah,
Which one is the script that we need to download, or the one that we are using?
What is what? Pardon me again.
Which one is the script that we are using right now?
The script is the one that's called, in bright space in the section of scripts, you'll see a script that's called, let me go to the script section. And the scripts, it is, I had located already. Let's see, conceptos básicos. Here it is, análisis escuelas. AM02 _ análisis escuelas.
Thank you, teacher.
Okay. So load it in your computers and we'll go over it. When you're ready, tell me you're ready. Any of you could tell me you're ready, that's it.
Ready, teacher.
Ready.
Okay. To erase, we don't have anything in the environment now. And it doesn't matter because we're going to do something very simple. When we run complex models, R runs in memory. So when we run complex models and with a lot of data, it is always good to erase the environment and start from zero so that we don't have things that we do not need when we are executing our code. So to do that, this is the instruction, rm list ls all true, or you can use this tool here. That's it looks like a, yeah, it looks like, no, it doesn't look like a scope. It looks more like a brocha, no? So, but it's that thing. That's to erase everything. I can use this thing, or I can just say rm list ls all equal true. Okay. So now let's install some packages. I forgot if I use all of these packages in this script. I don't think I do, but let's see. Now let's read the data. Well, I already finished installing the packages here. Okay, I already finished installing everything here. The scores, I'll read the scores. 60 observations for variables. If I want to view the file, I can view it. I can say view with capital case, view scores, and that will show me what the file has in another screen in this upper left panel. And it's okay in this case because we only have, say, 60 data, but if we have 2 million records, we want to avoid, say, the view file, okay? In this case, it's a small file. Normally, we do not use the view because if the file is too large, we don't want, we don't really want to see the whole thing. So we want to figure out how does it look like. We say head scores, and I can see here that's a data frame with 1, 2, 3, 4 columns, 4 variables. One is the subject ID, which is the ID of the student, the school, the English score, and the math score. Okay. We can also look at the structure of scores. And the structure, it tells me, notice that it doesn't say it's a data frame. It says it's a table. Table is in fact a data frame, and the table format is the one that has where we have an observation per row, and the variables are in the columns. Okay. For our practical purposes, this is just a data frame, and we'll treat it as a data frame. Now, in this script, I use ggplot to do some plots. ggplot is a language for plotting. At the beginning, it's a little more difficult to learn because we're not used to thinking that way. But ggplot, what it means is it's just a language that to build plots. It's based on layers. So we have a layer where the data resides. We have a layer where we have the layer where the data resides, the layer where we specify which type of chart do we have, in a layer that has other characteristics for the aesthetics of the graph and so on. There's by default, the plotting with ggplot2 gives a plot that's where the title is not centered and the background is gray. And I don't like that. So I usually this thing you can omit it now to see how the plots come normally from ggplot. Theme set, this is one of the layers that ggplot has, the theme. And I'm saying I want a theme in black and white. I want that my position, the title be positioned, the legend is positioned to the right, the legend. The plot, I want it justified in the middle. And the subtitle, I also wanted to just have it justified in the middle. Okay. If I do a theme set here, then I don't have to worry about doing this thing every time I produce a plot with ggplot. Okay. So for now, let's take it like that. If you don't want to run it, it's okay. It will not affect what you do later. The graphs will be different, will look different. Okay. I already said head scores. I already said head structure scores. And now, if you look at your data, the school, it's only 3 values. It tells me it's numeric, but it has 3 values. And it's in fact a factor because it's school 1, school 2, school 3. There's no order between the 3 schools. So I can treat that variable as a factor. And that's what I'm going to do. I'm going to define, I'm going to say scores, the variable school within the data frame scores, converted to be a factor of the same variable. Okay. So in the same place, I'm just changing the class of this variable. If you look at structure scores, it says here that scores, school is numeric 1 through 60. I'm going to make it a factor. Okay. And now I'm going to say, then I'm going to repeat this instruction, structure scores. structure, scores. And now it tells me that school is a factor with 3 levels. There's level 1, 2, and 3. Okay, so that and that makes sense for schools because there's no ordering in these numbers. It's just different schools. That's it. Okay, so I made it a factor now. Now I'm going to use a dplyr to recode the values on school. I'm going to make it so that when they see a 1, it's going to be escuela A. When they see a 2, it will be escuela B, and when it's a 3, it will be escuela C. Okay, so I'm gonna dplyr is a package that helps you manipulate data, and there's a function called recode dplyr. Again, I recommend you the 3 PDF files that are in the R section, in the R basic section in Brightspace, because I explain what dplyr, the different functions that have dplyr and how they can help us manipulate data. So I'm recoding the values or of the variable scores of school. I'm going to recode it, and then 1 is going to be escuela A, 2 is going to be escuela B, and 3 is going to be escuela C. Now, if I say head scores, now I have, instead of 1, I have escuela A here. Okay, I just recoded the values, and it's a factor. So now it doesn't matter that it's a string and it takes more spaces, more space in the computer, because treating it as a factor, it is only stored as a 1, and there's a relationship that ties that 1 to escuela A. Now I'm going to do a plot with the function ggplot. I'm going to plot scores is the data frame. The aesthetics tell me which variables I'm going to plot and what type of plot I want. Aesthetics tells X equals the English score, Y equals math score, and if you see here that this when I close this parenthesis, sorry, the one that's shaded, you cannot see it there. I don't know what's not, we're not showing the, oh, here it is. I was not saying. If you go through the second parenthesis here, this is closing the starting parenthesis that for the aesthetics. And then there comes the geometry. Which geometry? That's what type of plot do I want, and what characteristics I want in that plot. So my geometry is I want a graph of points. The aesthetics, I want to plot the color, take the color of the plot to be the school. This has to be a factor to use this aesthetics. So for the aesthetics, the color of the different points are going to be determined by the school. The size, that's the size of the point that is going to graph, and the alpha is a level of transparency for my point. Okay, and then if you can see, this starts adding. I start adding comments, and I can add something else from a layer that I already specified something before. And here I'm saying scale color manual, because there's a default for scale color for the colors. So I want to set it manual, and I want to do a scene green for a deep sky blue and a red one. That I put that in P. So P is a ggplot2 object. It hasn't shown anything. To show something, I say print P, and you can see the graph here. See, it's a scatter plot, but it used the colors sea green 4, which is this one here, deep sky blue, and red 1. There's these points are somehow transparent. There's a 0.6 transparency. I specified that when I set my theme set to put the labels on the right. So that's why I put school, Escuela A, Escuela B, Escuela C. English score and math score. I could also change these titles, okay? I can change it, and I didn't put an overall title for this graph. Okay. Now that's as you can see, there's what sort of things you were called to do in the analysis, and I'll let you discuss those things. We'll produce the graphs, and then you'll discuss this what sort of things you can infer from these graphs. It's we're now at line 50 in my script here. Let's take a break here. It's 10:55. Let's come back at 11:15. Okay.
Okay, teacher, thank you.
Okay, thank you.
Let me pause the recording. Bueno, entonces nos quedamos aquí, ya hicimos esta gráfica. Podemos mover aquí los tamaños o el porcentaje de transparencia sin problema. Le podemos decir aquí que lo quiero de 1 y un alfa de 0.4. Y no hay problema, repito la gráfica y ya hasta que veamos una gráfica que nos dé más o menos lo que queremos obtener, ¿no? Entonces ahí está la forma. Ahora hay otro paquete que cargamos ahorita que se llama ggpubr. Entonces en este paquete lo que tenemos es, nos facilita algunas cosas, algunos tipos de gráficas para hacer con ggplot. Entonces vamos a cargar la biblioteca y voy a hacer una función, voy a utilizar una función que se llama ggScatterHist. Que lo que me hace esta función me va a graficar, a ver, find function ggScatterHist, déjenme ver si instalé bien el paquete. A ver. No lo instalé. No lo instalé. Bueno, otra forma de instalar paquetes, no sé si lo vimos la vez pasada, puedo decir aquí install packages y le voy ggScatter, no lo encuentra. No lo encuentra. Mejor la descontinuaron. Déjenme checar aquí que vamos a darle aquí en la consola. Le voy a dar, vamos a decir que cancele aquí, le voy a decir doble interrogación ggScatter.
¿Para qué sirve el doble signo?
Para ver, por ejemplo, si con el signo, con uno solo, es como un help de lo que yo ya tengo entre mis bibliotecas y todo eso instalado. Pero cuando por ejemplo, si hay una función que no sé de qué paquete es y no está jalando, entonces le doy doble signo de interrogación y me va a decir que es de qué paquete. Por ejemplo, aquí si le dijera doble signo de interrogación ggplot, esto me dio un internal server error. Estoy teniendo este problema. Inténtenlo ustedes doble signo de interrogación ggplot, porque me estaba dando un error de servidor en algunas veces en algunas cosas que pregunto con el doble signo de interrogación. Entonces.
Y el signo individual, o sea, ¿te dice en qué tipo, si tienes errores de sintaxis o algo así, o no te dice tan específico?
Te dice la sintaxis ggplot. Es como el help. Aquí te dice
bueno.
la sintaxis que debes tener. Te dice datos, tal son, mappies, los aesthetics, el environment, ese rollo, ¿no? Y aquí te dice lo que son las diferentes cosas. Por ejemplo, este aquí de environment ya no se usa. Eso se utilizó antes de la evaluación de Tidy. Y ahorita no me está saliendo esta función de ggScatter plus, pero vamos a ver. Una de las ventajas con R es que luego Google es muy útil, muy útil. Vamos a verle aquí donde estaba. Es de ggpubr y no instalé ggpubr.
Prof, a lo mejor es porque arriba le marca que necesita instalar como otro programa donde dice package it's required. Nada, yo creo que es nada más darle install y ya a mí ya me corrió.
Sí, porque
Ah, ok.
yo sí lo
En
instalé.
en la línea amarilla que aparece en el script.
Ah, ok. Sí, no, ggpubr es el que no instalé. No sé por qué aquí me faltó. Vamos a ponerlo library. Quiero decir, es ggpubr. Es ggpubr, les dije, ¿ah? Install packages.
Y el otro paquete, prof, es ggp misc.
ggpmis, sí. Aquí
Y creo que te falta un paréntesis, ¿no?
me falta un paréntesis aquí. Y library.
Le faltó el
¿Algo?
install, la I en install, prof.
¿Mandé?
Le faltó la I en install, arriba.
Ah, sí, install. Cuando agregué el espacio, ¿sabes qué? Le tecleé la tecla de insert por accidente y no.
Y también el paréntesis
Y
del final.
también el paréntesis. Y ver dónde está. Y aquí no lo cerré. Y el otro mis, ¿verdad? Aquí está. Mis. Entonces se lo voy a dar con este. Tools, install packages. Uf, me está instalando cosas que no tenía. Ahora a ver a qué hora termina de instalar lo que tenía que instalar. Packaging.
Pero a mí me puso error en el instalar.
¿En cuál? ¿En el de ggpubr?
Sí.
Inténtalo con lo de tools. En install packages ggpubr. Aquí le das ggpubr.
Yo le puse directo, prof, en donde dice, en la bandita amarilla donde dice install,
Ajá. También
instaló
aquí.
directo los dos paquetes. Ajá.
Ajá. Aquí le dice install y ya se quita. Library ggpubr. Ya. Así el hist. Install en ggpubr. No está todavía trabajando acá. Cuando ven este circulito rojo, es que está procesando cosas. Entonces no les va a hacer caso. Cuando tienen un proceso que toma mucho tiempo y ya debió haber terminado, entonces lo pueden parar aquí. Si es un paquete que es altamente intensivo en cómputo, por ejemplo, una estimación de un red neuronal o un support vector machine, a veces si le aprietan aquí no funciona. Entonces lo que hay que hacer es darle control, apagarlos del sistema, cerrar R del sistema. Cuando esto no funciona, no hay manera. Vamos a ver a qué hora acaba. Si es sabido, lo pongo en el break. Uf, está eterno esto. Todavía le falta un buen, ya, y ya. Library. Ok, ahora ya me voy a ir a lo que quería hacer, que es el G-scatter hist. Y aquí lo que hace es, me pone la distribución, los puntos, la gráfica de puntos, tal como estaba. Las etiquetas las moví acá, a la parte de arriba, y aquí me grafica un estimador de la función de densidad de cada una de las escuelas, de los scores de las diferentes escuelas. Entonces aquí tengo, aquí me dice la distribución marginal de las calificaciones de inglés para las 3 escuelas. Entonces aquí podemos ver, por ejemplo, que en la escuela roja, que es la escuela A, las calificaciones tienden a ser más altas en inglés, las calificaciones de inglés. Y las calificaciones, fíjense que las calificaciones en las otras 2 escuelas, las calificaciones de inglés tienden a ser más bajas. Fíjense aquí cómo está la densidad. ¿Sí? Y mientras que en la distribución marginal de los scores de matemáticas, vemos que la azulita, que es la escuela B, tiende a tener mejores calificaciones, calificaciones más bajas en matemáticas, y las más altas en matemáticas pues andan bajonas en las 3 en términos de densidad, ¿no? Entonces, ahí me da la información, no tanto de cómo están las calificaciones distribuidas por escuela, sino también me da información de las distribuciones marginales.
Prof,
Aquí,
ahí a mí solo me salió una escuela. No sé por qué.
¿una sola escuela?
Ajá, de hecho, solo, o sea, los puntitos sí me salen todos, pero
Ajá.
las líneas solo me sale la verde.
Ah, caray. ¿Y tu comando de GG Scatter Hist está igualito a este?
A ver.
Tiene que decir cuál es tu X, cuál es tu Y, el color, el
Sí, sí está igual.
tamaño, etcétera. Y luego el margin plot, aquí en el margin le puse que fuera densidad, density.
Sí, sí está igualito.
¿Está igualito? Está raro. Está raro, ¿eh? Y un color que también así dice, los
Sí,
3
todo
colores.
está idéntico. O sea, o sea, me salen los puntitos y todo, y la línea verde nada más, no me sale la
Ah,
rosita ni el azul.
está raro, ¿eh? Si quieres
Ay,
lo
no.
vemos luego porque sí debería de salirte,
Va.
¿sale?
Ujú.
Prof, yo ya lo descargué, pero me pone que error en packages or namespace.
¿Cuál descargaste?
El Pulver.
¿Y qué error te da?
Error package or namespace load failed for ggpulver.
A ver, vete a Tools,
Ajá.
instálalo desde ahí.
Sí, es lo que hice.
¿Es lo que hiciste?
Sí.
A ver si quieres comparte tu pantalla.
Mm,
Ah, tengo que dejar de compartir yo. Listo.
Solo corro.
A ver, ahí te dio un error. Package on space loaded. Load failed for ggpub in load namespace. There's no package called car. Y a ver, vete a Tools y das la instalación de nuevo. En Tools.
Aquí le voy a instalar, ¿no?
Ujú, sí. Ya. Ya lo instaló, ya nomás da el library.
Aquí.
Ujú. Y la gráfica Gigi Scatter Hist.
Y sí, aparece.
Y en library, es que en library te repeló. Check. There's no package called car. ¿Alguien más le dio un error como este?
No, prof. A veces lo que pasa es que en la parte abajito de environment, donde dice files, plots and packages,
Ajá.
a veces tienes que buscarlo como manual y darle como en la palomita de que está activado.
A ver. Aquí.
Ajá, pues,
El Gigi Puber. Ahí está.
ahí, chance y ya con eso.
Ahora vamos a ver.
No. No, está raro. Si quieres también al final lo vemos,
Ok.
¿sí? Para ver qué está pasando, porque sí está raro. Debería de... Porque no te dio error a la hora de instalar el paquete. Bueno. Bueno, acá se fijan, le puse que las gráficas marginales fueran de densidad, ¿sí? Aquí podría ponerle que margin plot igual, déjenme ver si lo conoce así como box plot, no me acuerdo cómo se llama. Vamos a decirle box plot, a ver si me gráfica box plots. Ahí está. Entonces, en lugar de las funciones de densidad, me grafica las gráficas de caja. Que, por ejemplo, en este tipo de gráfica es más claro, ¿no? Aquí se ve, ¿qué podemos ver aquí? Primero, el spread, la variabilidad que tengo en los scores de inglés es muy grande en la escuela A. Es muy grande la variabilidad con respecto a la variabilidad que tengo en las otras dos escuelas. Tengo, está cargada a la derecha, es decir, tengo calificaciones más altas en inglés en la escuela A. Mientras que, por ejemplo, en la escuela A también, que es la rojita, las calificaciones también más altas en matemáticas ocurren para la escuela A. Aquí las variabilidades de las tres escuelas están muy parejas en los scores de matemáticas, pero vemos claramente que los scores en matemáticas tienden a ser mejores en la escuela A que en la escuela B, y estos a su vez tienden a ser mejores que en la escuela C, por cómo se ve la distribución de las calificaciones de matemáticas. Y en la marginal vemos que las escuelas B y C están muy parejas con calificaciones más en el lado bajo de inglés, y la variedad es muy grande, pero sí es la que mejor se desempeña en inglés. Entonces aquí podríamos ver que los que vienen de escuela A, tanto en inglés como en matemáticas, tienden a tener mejores calificaciones, ¿no? Tanto en inglés como en matemáticas. Ahora, también a veces es útil graficar en múltiples paneles. Aquí voy a utilizar ggplot, y aquí se fijan, aquí le voy a poner una cosa que se llama facet wrap. Entonces, para que me haga paneles por la escuela, y que esos paneles me los ponga en 3 columnas y en un renglón. El color va a ser, estos son los colores, que es lo que está utilizando. Lo dejo en P2, luego print P2, y lo que me va a hacer es me gráfica las escuelas. Me pone para la escuela A, el score de matemáticas contra el score de inglés, en la escuela B, en la escuela C. Entonces, aquí, por ejemplo, en la escuela A vemos que a mayor score en matemáticas también corresponde mayor score en inglés. Lo opuesto aparentemente está pasando acá en la escuela B, y la escuela C como que casi no importa. Aquí me puso una línea suave que me ajustó una función que se llama una función de spline para suavizar los puntos. No me puedo pedirle que me grafique una línea recta en lugar de eso. ¿Sí?
Pero no te da mucha información la línea recta, ¿no? O-
Mira, esta también te da mucha información porque ves que algo está pasando aquí, que hay una bajada y luego sube otra vez la relación. Ves que no es una relación muy lineal.
Es algo como cúbico, ¿ok?
Sí, ese podría ser una relación cúbica, una cosa así. Entonces, para cierto nivel de grados de calificaciones de inglés, mientras más sube la calificación de inglés, más baja la de matemáticas. Pero hay un rango de calificaciones de inglés para los cuales mientras más sube, la de matemáticas o sube o tiende a mantenerse. Aquí se pueden apreciar que hay como dos tipos de comportamiento, ¿no? Aquí en esta gráfica en particular se pueden apreciar los dos tipos de comportamiento. Parece que aquí podría yo dibujar una línea recta. Fíjense, aquí podría yo poner una línea recta. Aquí. Porque de aquí para acá,
¿En qué parte del script vamos? Porque creo que yo no tengo esta parte.
vamos en la página, en la línea 73, y corrimos la 69. Esta que
Ah.
dice P2.
Creo que yo tengo hasta la 59.
¿Ah, sí?
Ujú.
¿Lo bajaste de Brightspace?
Sí, no
No,
sé.
sí está completo,
Está
Farid.
completo,
¿Quieres
profe.
que te lo reenviemos?
A ver, tal vez lo borré. Sí, por favor.
Ok. A ver, aguanta, si quieres te lo reenvío por WhatsApp.
Gracias.
De nada. Prof, y por ejemplo, en esta gráfica podemos ver que en la escuela C, su calificación máxima en inglés por lo menos es el 70
Ajá,
y en matemáticas más o menos un 38, ¿no? O
así
sea,
es.
no llega ni al 40.
Sí, aquí, fíjate, en matemáticas, en esta escuela C, bueno, tienes aquí este que llegó a 40 y algo, ¿no? De 48. No, sí, no llega ni al 50. Y aquí aparentemente no hay relación, porque esto casi es una línea recta horizontal. Entonces no se ve que hay una asociación fuerte entre el score de matemáticas y el score de inglés, mientras que aquí sí, aquí sí pudiera parecer que hay una relación a mayor calificación en inglés, mayor calificación también en matemáticas. ¿Sí? Son del tipo de cosas que podemos inferir del análisis gráfico. Y vemos que sí hay, si les preguntaran, nada más en lo que hemos visto hasta ahorita, ¿hay diferencias entre las escuelas? ¿Hay diferencias? ¿Qué contestarían?
Sí, sí hay.
Que sí,
Sí
Sí,
hay.
sí hay
bastante.
diferencias, ¿no? Sí hay
Ujú.
diferencias definitivamente en las tres escuelas y pinta como que la escuela A los prepara mejor a los muchachos para que tengan mejores calificaciones. Ahora esto es en diferentes paneles. Estamos graficando X contra Y en tres paneles diferentes. En tres paneles diferentes. Esa es la que corrimos ahorita. Ahora, aquí lo que voy a hacer, fíjense, acá le puse en método, le puse Geom Smooth. ¿Sí? Aquí le voy a poner en Geom Smooth también, pero le voy a decir que utilice el método de la regresión lineal. Entonces aquí sí me va a poner una línea recta. Entonces le voy a decir P3 es esta gráfica. Y si ahora la gráfico me va a dar la relación en línea recta y también eliminé las zonas de confianza, las bandas de confianza. Eso lo eliminé aquí con esto. SE, Standard Error. La otra me puso las bandas del error estándar. Y si no quiero que aparezcan, le digo SE equal false. Entonces ya veo cómo se comportan las calificaciones. Entonces aquí, si fuera a ajustar líneas rectas, claramente aquí a mayor calificación de inglés, mayor calificación de matemáticas, aquí es lo opuesto, y aquí pues casi no, esta pendiente ya es muy chiquita, ¿no? Es muy cercana a cero. Entonces son formas de obtener información de los datos en forma gráfica, ¿no? Estadística descriptiva, puramente descriptiva. También podemos, aquí fíjense, aquí se ajustó una línea de regresión. Entonces, también podemos agregar la línea de regresión para que aparezca en la gráfica. Entonces, aquí todo esto no cambia. Jump point, scale color, todo es lo mismo. ¿Sí? Path drive to school. Y aquí le estoy diciendo voy a hacer esta en GD primero. Y es la misma gráfica que vimos sin las líneas, ¿no? Aquí más le quité las líneas rectas. Ahora las puedo agregar ahora y agregar también el coeficiente de correlación. Entonces con esto le digo, escribo una formulita, le digo y como función de x, la fórmula, así le digo que es la fórmula, y como función de x, y hago el stat smooth, le hago el método de mínimos cuadrados, el label.y para la etiqueta de y igual a 4.5 y luego le pongo aquí que ponga la ecuación stat poly y me pongo en la ecuación con el color de la escuela, va a utilizar el color de la escuela, la etiqueta la etiqueta va a estar a la altura del 3.5 en las yes. Vamos a decirle, ay, ¿qué hice? Fíjense qué hice. Control Enter. Ahí está. Entonces aquí me dio la gráfica. Le quité lo del SE, que fue igual a false, para que le pusiera las bandas de confianza. Y me está poniendo aquí la ecuación de regresión. En la misma gráfica. Y acá abajo me da el coeficiente de correlación. Y el coeficiente de determinación. Si ya toman regresión, ya saben que R cuadrada es el coeficiente de determinación, y aquí el ρ me está significando la correlación. Perdón, no, este es P. Este es R está utilizando para la correlación, ya me acordé, R está utilizando para la correlación, es 0.57, aquí es menos 0.57, fíjense, esta pendiente es la misma que esta, pero para el otro lado, ¿no? Es 0.57, esa es la correlación entre X y Y para estos dos casos, y aquí es 0.11. Esta P que está aquí me está dando el p-value para probar la hipótesis de que el coeficiente de correlación es 0 contra la alternativa de que es diferente de 0. Entonces, el p-value aquí es 0.009, quiere decir que sí hay suficiente evidencia para decir que el coeficiente de correlación es diferente de 0. Aquí también el p-value es 0.009. Entonces quiere decir que no hay suficiente evidencia para decir, que existe suficiente evidencia para decir que el coeficiente de correlación es diferente de 0. En cambio, en este caso, el p-value es 0.63. Entonces, como es un p-value muy grande, aquí el coeficiente, lo que podemos inferir de aquí, si hubiéramos probado la hipótesis de que el coeficiente de correlación de la escuela C entre los scores de matemáticas e inglés es igual a 0, contra la alternativa de que no es igual a 0, no podíamos rechazar la hipótesis de que es igual a 0, porque el p-value es bastante grande, mucho más grande que el 0.05 que normalmente usamos para ver si rechazamos o no una prueba de hipótesis, una hipótesis. Entonces, son diferentes formas de graficar y de obtener información de los datos que me ayudan a entender qué es lo que tengo. El análisis descriptivo se vuelve un componente muy importante siempre en cualquier análisis multivariado. ¿Sí? Esto es fácil hacerlo, tenemos 3 escuelas y nada más estamos viendo 2 variables. Si estuviéramos viendo, si P en lugar de ser igual, I'm sorry, I forgot I was teaching in English. Sorry about that. If the number of variables was different than 2, it was, let's say, 4 or 5, then graphically it's going to be a lot more difficult to detect any differences between the different schools. However, with only 2 variables, English score and math score, there's a lot of displays, graphical displays that can help us understand what's going on and how these different schools are giving different results in their students once they start college. Okay? So I'm gonna quit this thing and I'll go back to the presentation. So here's a conclusion. What could you conclude? That school A, it seems to be a better school to prepare the students better for college and than any of the other two schools, for example. Okay. Now, if we have p-variate random variables, then we'll have their density functions will be in p-dimensional space, okay? Because we have p random variables. Now let's look at some of the theory. Let's denote by y the vector that has y1 transpose, yp transpose, and so on. Remember that y1 is a vector of n rows in one column, which is the variable 1. The second one is, again, n rows in one column, which represents variable 2, and so on. Then the cumulative distribution function of y is defined as we do it in the univariate case. It's the same thing. It's a probability that the vector y is less than or equal than some specific vector lowercase y, okay? And since these are vectors, this probability is the probability that y1 is less than or equal than little y1, y2 less than or equal than little y2, and yp less than or equal than little yp. Now, for a continuous random variable, random vector y, there is a non-negative density function f such that the distribution function of y can be expressed as the integrals from minus infinity to y1, minus infinity to y2, minus infinity to yp, which are these values here, because we want to be less than or equal to is the probability that y is less than or equal to that vector that contains y1, y2, and yp. And that will be this integral of the function. This is the joint density function of u1, up, du1 with respect with the same variables, the 1 through the p variable. For simplicity, we can write this thing down as an integral from minus infinity to the vector y. We know that this is the notation, but we know that this implies p different integrals of the density function. And that will be the probability that y less than or equal to little y, okay? That's this probability. Just like in the univariate case, the cumulative distribution function is denoted usually by CDF, is differentiable, and the density function, the multivariate joint density function f of y, is is formed by the partial derivatives of f of y with respect to y1, y2, and yp. Okay, so it's just like in the univariate case. For a continuous variable, the CDF, the PDF is going to be the derivative. Now we have several variables, so it will be the partial derivative. The p is because we have p variables of the cumulative distribution function, differentiating with respect to y1, y2 up to yp. Now, if we were to partition a vector y in two parts, y1 and y2, y1 would have k variables. So y1 will be residing in Rk because it has k variables, and y2 has p minus k variable. So that because remember the vector y is p by 1. So y1 will be k by 1, and y2 would be p minus k by 1. then we can compute, it doesn't matter what the value of k is, we can split it into the first variable and the rest, or the first two variables and the rest, and so on, doesn't matter. For any k, the marginal distribution of y1, that is this partition that we did here, if we want to obtain the marginal distribution of y1, we denote that by f sub y1 of little y1, okay, so for some particular value little y1, that will be the probability that y1 less than or equal to than y little lowercase y1, and that is the function, the cumulative distribution function evaluated at y11 to up to y up to k, and then for the rest of the variables, for the p minus k, here we have p minus k variables will be integrated into infinity. Okay, that's how we obtain the density, the marginal density function for y1. And the marginal density function, this is the marginal distribution function, this is the marginal density function, is just going to be the integral of f of y1, y2, but differentiated with respect to y2. Okay, we remove y2 and integrate over the function, the density function for the y1 vector only. And that works for any partition that we do of a random vector. And the conditional PDF of y2 given y1, there is a conditional distribution density function for y2 given y1, given that y1 takes a particular value, that is that the vector takes a particular value, a particular vector of values. That density function, the conditional density, is given by f of y2 given y1 is just the joint density function divided by the marginal density function of y1. And I believe that this is, you see some of this stuff in statistical mathematics, in the statistical mathematics class. Okay, so it just, I'm just removing, let's say, one way of saying it is I'm going to remove the effect of y1. So given that y1 takes a particular value, that's a constant already. So I take the density, the joint density function divided by the marginal. This is, and remember, this is the marginal density function for y1. Now, y1 and y2, the two subvectors of y, are independent if and only if, this is an if and only if condition, the joint density function of y1 and y2 is the product of the marginal densities. Okay, so y1 and y2 are independent if and only if the joint density of the two vectors is the product of the marginal densities of each one of the random vectors. Okay, and this is an if and only if condition. This is important to remember. This is an if and only if. Therefore, if y1 and y2 are independent, their PDFs are equal to the marginal PDFs, right? So if they are independent, then f of y1 given y2 doesn't depend on y2. It's just the marginal of y1. Okay? If f of the conditional density of y1 given y2 will be the marginal density of y1, if that happens if y1 and y2 are independent. Okay, because we know that if y1 and y2 are independent if and only if the joint density is the product of the density of the marginal densities, and this conditional distribution, conditional density of y2 given y1 is going to be the marginal distribution of y2 if they are independent. If y1 and y2 are independent, their PDFs are equal to their marginal PDFs. So far, so good? We're okay up to this time?
We're
Yes,
okay, teacher.
Yes,
Okay.
teacher.
Yes, teacher.
Okay. Now let's, okay. So but this is an important result. If we were to compute the marginal distributions of y1 and y2, and if we see that those marginal distributions are the same as the conditional distributions, that happens when y1 and y2 are independent, okay? Now, one of the exercises that we're going to be doing is we're going to be working with the Swiss bank notes. These are estimates of the univariate densities for variables inner to lower and inner to upper, okay? So there's two variables. Remember, we talked about these Swiss bank notes that have several dimensions that are measured on them. One of a couple of these dimensions are the distance that there exists between the inner frame to the lower, the inner edge, let's say, to the lower frame, and the inner to the upper frame, okay? These are the density functions. These are marginal density functions. Ignoring the fact, we know that some of the nodes are legitimate and some are not. We're not ignoring that fact now. So these are the graphs of the estimates of the density function for the inner to lower distribution and the inner to upper. Now, if we distinguish which are the false and which are the authentic nodes, Swiss bank nodes, this is the density function. The red part here is the density function of the legal ones. Okay, the blue is the one these are the counterfeit. Okay, counterfeit is 0 is legal, 1 is counterfeit. So we can see that there's a difference. They're distributed different. The distribution of the inner to lower dimension seems to be shifted to the right for the counterfeit Swiss bank notes, whereas the distribution of the same variable inner to lower for the legal notes, for the correct, for the valid notes, let's say, is more shifted towards the left. And there's a few cases here. There's some little skewness here in this graph. And we also see a different behavior in the inner to upper, because we see that on the right-hand side of these two plots, the right-hand side, we show that the inner to upper, the counterfeit nodes tend to be shifted, their measurements a little bit to the right, but there is more overlap. If we were to look at the overlap in distributions for both cases, not see here what's the overlap that we have, and here what's the overlap that we have. Based on this, these are the distributions of those measurements. Based on this, if you wanted to discriminate among between the counterfeit bills and legal bills or notes, which dimension would you choose? You were suppose you are forced to choose one dimension to be able to determine if a note is false or if it's legit. Which of the two dimensions, which of the two measurements would you choose?
The left one.
The left one, right? Because the overlap between the two distributions is
less.
smaller, so
Yes.
it will be easier to discriminate between the false and the legal notes.
That's right.
Okay. Now,
One doubt. Where measure the length of the symbols of the bills, or what we are measuring?
we're measuring, let's suppose that this is the bill. Let me draw the bill here. That's a bill, and there's an inner frame here. Okay, this one on the left, inner to lower, is measuring this distance. Let me change color here. This distance, and the inner to upper is measuring this distance. Okay, and we have other measurements in the data set that we'll be analyzing. We have other measurements. We have the measurement of the diagonal, which measures from here to here. Okay, and we also have measurements on this side and on this side, and also this side here. Okay, but we're taking now these two, and the measurement that seems to discriminate better between the false nodes and the legal nodes seems to be the inner to lower between these two. Okay, we haven't looked at the others. We're going to be looking at the others also.
Okay, thank you, teacher.
Okay. Okay. And now let's look at this graph. This is a joint density function for the two measurements, okay? The inner to lower and inner to upper. If this is the product of the univariate PDFs, okay? This is the product of the marginal PDFs. And this is the joint estimate, this is the non-parametric estimate for the joint distribution of the two measurements, inner to lower and inner to upper. Would you say that inner to lower and inner to upper are random variables who are independent?
Which and which?
The two measurements that we have, inner to lower and inner to upper, are they independent?
No.
No.
No, because if they were, then the product of the univariate PDFs, the product of the marginals, would look exactly the same as the joint density. So that we know that they are not independent because the joint density looks very different from the individual, from the product of the univariate PDFs. Okay.
That's right.
Okay. Now let's start talking about the multivariate normal distribution. Let's see, it's 12. Let's take the second break here. We'll come back at 12:15. Okay.
Okay, thank you.
No,
Thank you,
Thank you, teacher.
no, thank you.
Thank you, teacher.
We'll see you in a few minutes. Okay. So let's look at the normal multivariate normal distribution. Just as in the univariate case, a lot of the inferences that we make in the multivariate case are based on the normal distribution. Now it's the multivariate normal distribution, and because of the things like the central limit theorem that you studied in statistical mathematics, apply or generalize to the multivariate case. We will not go into the theory, but essentially the central limit theorem that you know works in the univariate case, something like that will work also in the multivariate case. Now, what characteristics does it have? The multivariate distribution is completely described by its first two moments, just as in the first case, in the univariate case, the mean and variance determine completely the normal distribution. Well, in the multivariate case, the vector of means and the variance covariance matrix determine completely a normal distribution. In the case of the normal, if the variables are not correlated, if their correlation is 0, they are independent. We also have the result that linear functions of multivariate normal variables is also a multivariate normal distribution, is also a normal distribution. So you have a linear combination of the p variables that we have that new variable is also going to have a normal distribution if all of the others have a normal distribution. Even if the data does not have a multivariate distribution, this is in fact a useful approximation. In fact, this comes from the extension of central limit theorem to the multivariate case. Okay, so when we make inferences that involve the sample means, then the central limit theorem makes it appropriate to use a normal distribution to do those inferences, to use that distribution because of that central limit theorem. Now, what's a PDF? The PDF of a normal multivariate normal is given by this expression. As you can see that it's very similar to the univariate PDF, but there's some changes here. Here, for example, we're dealing with vectors. So the exponential is the exponential of minus y, which is the random variable, the random vector, minus its mean, transpose, times the inverse of the variance covariance matrix, times y minus its mean divided by 2. And then that's multiplied by 1 over the square root of p raised to the p power, to the pth power, and the determinant of sigma to the 1/2. Okay, so it looks very similar to the PDF of the normal distribution in the univariate case. In the univariate case, remember that in the univariate case, if x was a normal with mean mu and variance sigma square, then its PDF was what? Was 1 over the square root of p, square root of 2p, and then what was it? It was sigma, okay, the square root of sigma quadrada, of sigma squared, and then it was the exponential of minus x minus mu over sigma squared. Okay. That was the PDF in the univariate case. So it looks very similar. Now we're dealing with vectors. Here, remember, y minus mu is a p minus 1 vector. So y minus mu transpose is a 1 by p vector. Y minus mu is a p by 1 vector, and sigma is a p by p matrix.
So that's just one, no?
Hmm?
Oh, p by p?
Yeah, sigma to sigma, the variance covariance matrix is p by p. So we have a 1 by p times a p by p times a p by 1. This will give me a scalar, right? This is a 1 by 1. This is scalar, the result of this.
See.
Okay? Now, the bivariate PDF looks like that. We'll see other examples of bivariate PDF. If we, this is a contour plot. Contour plot is essentially like if we were taking slices of this distribution, we take a slice here and see how it looks, and this is this outer curve. Then we take another slice. I'm sorry. Sorry. So we slice it. Thank you. We slice it in different heights, and we project those slices into an x by y plane, and that's what gets us the contour plot. Okay. We'll see several examples and see how changing the variance covariance matrix changes the figure, the shape of these contour plots. See, for example, this is a normal distribution where sigma equals to the standard deviation of both variables is the same, and there's zero autocorrelation. then what we get as a counterplot are circles, okay? Because the autocorrelation is 0. So that means that they are independent. X and Y are independent. Because if they are normally distributed, the fact that the correlation is 0 implies independence. In this other case, we have both standard deviation are the same, but draw the correlation is 0.75. So we'll see ellipses like this with this direction. The larger the X is, the larger the Y. And again, this is the contour plot. Then in the next example here, we have both standard deviations are the same with correlation is minus 0.75. The only thing that changes looks very much like this one here, but the direction changes because the correlation is negative.
So if we can see like the perfect circle right there, that means like they're independent.
In this one here,
Uh-huh.
first, yeah, they're independent because the correlation is 0.
Yeah.
Okay. And as you can see, this will be at the 80%. If you were to build an 80% confidence region, that region would be represented by this circle here. By this circle. I lost my mouse. Okay, here. And in this case, this will be the 80% confidence region. These will be the 95% confidence region. So if we were to take a sample and build a confidence region for the mean vector, it would be something like this. It will be an ellipse depending on what the correlation is. That will be the direction of the ellipse. But now instead of talking about confidence intervals, we talk about confidence regions. Here we have a case where the first variable has a variance twice the variance of the standard deviation, twice the standard deviation of the other variable. And these are the contour plot. This is the contour plot for this particular distribution. And this is where sigma is the same case, the two variances, one standard deviation is twice the other. Now the correlation is 0.75. Okay. And this is a case where the same relationship 2 to 1 in terms of the standard deviation, a correlation of minus 0.75. Okay. That you have the script to generate these graphs. That script, you have it in Brightspace. Let me show you where. Let's see, in 002. Why I didn't put it? No, I guess I didn't put it in Brightspace, but it's just generating those graphs. I'll add it here to the scripts. It's a script that will be called. I'll add it now. Hold on a second. Let me go to my directory. Our scripts, and I'll add them now. Bivariate normal distribution and distributions. I'm going to put them. This will be in the script section. Now you'll find them at the end. I'll move it later. I'll move them to the beginning, so it goes with this thing. So it's this script. That's to generate these normal distributions, and this is another script to where you remember the Swiss bank notes that I showed the densities and the contour plot and the densities, and also the product of the densities for both variables. Okay, that script, this script is the bivariate and normal bivariate distribution. Okay, so this here we graph. Let me see. Right now, this is a bivariate normal distribution. Okay, this script I took it from Ellen Cohen. It's at Central Michigan University, and that generates the graphs. You can vary the values of sigma 1, sigma 2, and the correlation, and you can see how the shapes change for any combination that you have of sigma 1, sigma 2, and the correlation. So I will not go over that thing. This other script is the one that I use to generate the density functions. Okay. So I have the function kernel smooth, which this function estimates the kernel. It provides the kernel estimate of the density function. And grid extra, I'll go over very fast. Let me see if it's worth going over this thing. This is just the plots that I showed you. You can run the script later. I already have set the script. I mean the working directory. I installed most of the packages already, and let's see. I think I believe I haven't installed Crane Smooth already. Anyway. And here's where I plot the univariate estimates. Okay, so you can run this script later. And during the univariate estimates, these are the graphs. All right, I'm showing here something that I should have told you before. Let's see. I'll follow the script. It's worthwhile following. This is the data is in SVN, okay, and it's separated by tab. So that's why I read it like this: separated by a tab. And as you can see, we have case one tab. It's not producing anything here. No. It is here. It must have been giving me an error sometime earlier. Now here it is. SVN has the length of the bill, the left height, la altura, how high it is on the left side, the right height, the inner to lower, the inner to upper, the diagonal measurement, and whether the node is counterfeit or not. 0, it's not counterfeit. 1 is counterfeit. So try to follow this script. I'll if there's time today, I want to finish with the normal distribution, and if there's time, we'll go over this thing with this script. But now let me try to finish with the normal distribution. I'll continue here. So you can produce for any combination of the sigmas and the coefficient of correlation, you can generate the plots, okay, with the script that I just put into bright space. So the properties we said that linear combinations of a normal are normal. As in the one-dimensional case, we can work with standardized variables. So we can convert any normal random variable by subtracting its mean. Remember that in the univariate case, we subtracted the mean and divided by the standard deviation. And we got a standardized normal random variable that had a distribution which was normal with mean 0 and standard deviation 1. But we do the same thing in the multivariate case. How do we standardize it? We take y minus mu, the vector y, minus its mean, but we pre-multiply that vector by sigma to the 1/2. Sigma is the variance covariance matrix, the inverse of sigma to the 1/2. Sigma to the 1/2 is the matrix such that when you multiply sigma to the 1/2 times sigma to the 1/2, you obtain sigma, which is the variance covariance matrix. Okay, so it's like the root of the it's not the it's as the equivalence of the root of a variance, let's say. When we invert this thing, Remember, in the univariate case, we take x minus mu, subtract by sigma, divided by sigma to standardize. Well, here we're dividing by sigma to 1/2, right? Which is the sort of the square root of sigma. So if y has a normal distribution, a p-variate normal distribution with mean vector mu and variance covariance sigma, then this standardized variable has a normal distribution with a vector of zeros as the mean, with mean 0, and variance covariance matrix equal to the identity matrix. That is, all the covariances between any pair of variables are 0, and in that diagonal we only have ones, which are the variances of each of the variables. Okay. Remember that in the univariate case, when we have a standard normal and we square it, we obtained a high square distribution. Okay, when we squared an univariate normal. I don't know if you remember that, but if Z was a normal distribution, Z was a normal, let me put it just to emphasize that it's univariate. I'll say that Z, the one-dimensional Z, a standardized variable, was standardized by taking x minus mu divided by sigma, and it had a normal distribution with mean 0 and standard deviation 1. When we took that variable squared, that had a high square distribution with 1 degree of freedom. Well, the extension to the univariate case, if we take the product of Z transpose times C, remember here we're dealing with vectors, so in high square is a distribution for a univariate variable, random variable. So if we take Z prime Z, the standardized vector C transposed times Z, then that's equal to y minus mu transpose times sigma inverse, because when we multiply sigma to 1/2 by sigma to the 1/2, we obtain sigma. So it's the inverse of the variance covariance matrix times y minus mu. This has a high square distribution with p degrees of freedom. So here it was with 1 degree of freedom because we had one variable. Now we have p variables, and when we take their dot product of the variable with itself, with the standardized normal with itself, then we get a high square with p degrees of freedom. Okay, that's another important result for the multivariate normal. What other properties? The marginal distributions of any subset of that vector, that random vector, are normal. So if the random vector has a normal distribution, any subset of that random vector will also have a normal distribution. So if we divide the vector in the first r variables and then the last r minus p minus r variables, then the distributions of y1 and y2 will be normal. So if this is the distribution of y, which is composed of y1 and y2, then the mean vector is mu1 and mu2. We decompose the variance covariance matrix also on sigma 1,1, sigma 1,2, sigma 2,1, and sigma 2,2. Sigma 1,1 is the variance covariance matrix of y1. Sigma 2,2 is the variance covariance matrix of y2, and sigma 2,1 and sigma 1,2 are both are the variance covariance matrix between the variables in y1 and the variables in y2. Okay. If this is the case, if y is normal, if this is normal, then y1, this part, is normal with r-dimensional normal, because y1 has r elements from y1 to yr. So it's an r-dimensional normal with mean vector mu1 and variance covariance matrix sigma 1,1. and y2 will then have a normal distribution of in dimension p minus r with mean vector mu2 in variance covariance matrix sigma to 2. Now, so what this says is if I have a vector that has a p-variate normal distribution, and I split the vector, or I take any of the variables of that vector, then that variable will have a normal distribution. The opposite is not true. Okay, the opposite is not true. That is, if each yi is normal, this does not imply that y, the whole vector, is normal. Okay, so if the joint if the vector y is normal, any subvector of that vector will also have a normal distribution, whether univariate if we only take one element, of multivariate we take more than one element. The opposite is not true. So if I have a random vector and each of the elements of the random vector are normal, that does not imply that the joint distribution of y is normal. Okay? Now let's assume that we partition the vectors in two parts, I mean the y and x, and we call it mu sub y, the mean value of the vector y, mu sub x, the mean value of the vector x, and the covariance between y and x will be the variance covariance matrix of the y, variance covariance matrix of x, and then of the diagonal we have the variance covariance matrix between the elements of y and x. Now, if y and x are independent, if the variance covariance matrix equals 0, if we're assuming that there is normality, okay? Now, if two variables are independent, and the covariance between those two variables is 0, there will be if two variables are independent, then if that will happen if the covariance is 0 in the case of normal distribution. Okay, that's only in the case of normal distribution. It is not true for normal variables. Okay. This is true for all variables. Y and x are independent if the variance covariance matrix is 0, and the two variables are independent if sigma jk is 0, which is not true for non-normal variables. Okay, if they are normal, independent, there will be the conditions of equivalence and covariance 0 will be equivalent if they are normal. If the joint is normal, the joint distribution is normal. If both are not independent, if y and x are not independent, then y given x is a multivariate normal with this mean value, which is mu of the y variables plus sigma yx, sigma xy inverse times x minus mu x, and this will be the covariance of y given x. Okay, if the y and x are not independent. Okay, the conditional distribution will be a conditional normal with a normal with expected value of y given x equal to mu sub y plus, so it's not mu sub y alone, it's mu sub y plus this variance covariance matrix yx and xy inverse x minus mu sub x. The covariance of y given x is this expression here. So these are properties of the multivariate normal distribution. Since we never know the mean and never know the variance covariance matrix, the population variance covariance matrix, we estimate them. Okay. So if y is normal with mu, vector mu, and variance covariance matrix sigma, then we estimate mu by y bar. And y bar, the sample mean will have a normal p-variate normal with mean mu and variance covariance matrix sigma divided by n. Okay, it's the same thing as in the univariate case. Okay, in the univariate case, if we have a random variable x that has a normal distribution with mean mu and variance sigma squared, then the mean of a sample taken from that distribution will have a normal distribution with the same mean because it's an unbiased estimator, and variance equals to sigma, the variance of the original variable divided by n. If y is not normally distributed, and this is the equivalent of the central limit theorem for the multivariate case, if y is not normally distributed for large n, central limit theorem, for large n, y bar will be approximately a normal distribution, a p-variate normal distribution with mean mu and variance covariance matrix sigma divided by n. So it's the extension of the univariate result to the multivariate setting, to the p-variate setting. Okay. Therefore, if n tends to infinity, square root of n times y bar minus mu will tend to a multivariate normal with mean 0 and variance covariance matrix sigma. Okay, all we're doing is putting that here we divide by n, but this is a variance covariance matrix, so we multiply by square root of n. It's the same thing that we did in the univariate case. Okay, and that's again the central limit theorem. Okay, if regardless of the distribution of y, if n is large, then y bar will be approximately a normal distribution, p-variate normal distribution with mean equal to the mean of the population, and the variance covariance matrix equals to the variance covariance matrix divided by n. Then the random variable w defined by n minus 1 multiplied by s, which is the sample variance covariance matrix. This w is said to have a Wishart distribution with parameters n minus 1 and sigma, which is the variance covariance matrix of the original variable. Okay, so this is the extension to the multivariate case, and the Wishart distribution is essentially the multivariate equivalent of the chi-square. Okay, because remember in the univariate case, sigma squared, s squared, which is the estimate of sigma, divided by multiplied by n minus 1, and for the unbiasedness characteristic, will have a chi-square distribution. Now, the multivariate equivalent of the chi-square distribution is the Wishart distribution, which is the distribution of n minus 1 times the variance covariance matrix, the sample variance covariance matrix. Okay. We will not be using much of this because we will not be doing a lot of hypothesis testing. It's just important for you to know that there's extensions for the chi-square distribution to the multivariate setting. Now, the problem of assessing, some of the procedures we'll be using assume that our variables have a normal distribution. Now, to assess multivariate normality is a lot more complicated than assessing univariate normality. Remember, we said that multivariate normality implies individual normality, okay? That's true. If we have a vector which is multivariate normal, then any element of that vector, any variable of that vector will also have a normal distribution. Okay, multivariate normality implies individual normality. When we have several variables, assessing whether one by one, if they have a normal distribution, does not assure us that the vector has a multivariate normal distribution. unless the joint was already a normal distribution. Okay, so when we have several variables, one by one, we should not only, that's not the only approach to show normality of the vector, because the variables may be correlated, and individual variables normality, this is the most important reason, individual variables normality does not imply multivariate normality. Okay, so we can do QQ probability plots to investigate univariate normality. If we find that all the variables have normal, close to a normal distribution, we cannot infer that the joint vector, when we put all of them together, they will have a normal distribution. However, testing for multivariate normality becomes very complicated. It's a lot more complex. There have been several tests that have been developed to test multivariate normality, but they are not very powerful. Okay, so what we do in practice is we just check for the variables to have roughly a normal distribution. And although that doesn't guarantee that we have multivariate distribution for the whole vector of variables, we feel comfortable with using the results from the normal distribution to do inference and test a hypothesis and so on. We will be using, if we start charting our graphs, we saw a histogram or density estimate of each of the variables, and we observe that they do not look like a normal. They are far away from the normal. Maybe they are very skewed or whatever. We can transform them to normalize the variable. And the most popular transformation, because in fact it's very powerful, this transformation is the Box-Cox transformation, which is defined by y to the lambda minus 1 divided by lambda, for lambda different from 0, and natural log of y for lambda equals 0. So what's essentially done is, for different values of lambda, you assess the distribution of the variable. So you take a grid sufficiently fine for lambda and check for normality, transforming the variable, and the procedure, what the procedure returns is the value of lambda that gets those variables to be as close as possible to a normal distribution. This is the Box and Cox family of transformations. To find out what's the value of lambda, in fact, we use the log likelihood function. We compute the log likelihood taking lambda as the parameter we want to estimate. That will be minus n over 2 times the natural logarithm of s squared sub lambda. So we need, for each lambda, we need to calculate this variance for each lambda, and then lambda minus 1 times the sum of the logs of y sub I, and then this s squared sub lambda is an estimator of the variance of y to the parenthesis lambda. So for the different values of lambda, we calculate that, and we choose the lambda that maximizes the log likelihood. Okay. For the multivariate case, we select a vector of lambdas. The lambda that we choose for one variable is not necessarily the same as the lambda that we choose for a second variable, and so on. So for the multivariate case, we select the vector of lambdas that maximizes this expression. Okay, this is the maximum likelihood estimate of the variance covariance matrix of the transformed observations. Is this denoted by S of L? That's an MLE estimate. Okay, so that's a vector of lambdas to achieve the transformation. And of course, doing this thing by hand is not feasible, but any software can work, has the Box-Cox transformation to try to find what the right values of the lambdas are. Okay. And univariate case. Now this is another important thing. So let's see. It's 10. It's 8 to 1 minus 4:1. Let me stop here. If you can turn on your cameras, that'll be great. To tell me if there's any doubts, questions. I will stop where I put a mark where we stopped so that I remember where I left it. And I'm gonna just put a little mark here. That's it. Okay. Are there any questions, comments? No? Okay. Please go over the script to generate the normal distributions. You can play around with sigma 1, sigma 2, and rho. And also the other script to do so that you can see how to estimate the univariate densities and how to estimate the multivariate density. The functions are there to do it. So go over those scripts. I will not go over them in class, but it's important that you review them, and that will give you a feeling of what sort of things you can be doing to explore this multivariate world. Okay, so that's good. Okay, guys. Well, thank you very much for your time, for your patience. We'll see you then next Monday. Have a good week. Have a nice week. Enjoy it.
Thank you, teacher. Can you upload
Take care.
later the video to YouTube?
Oh yeah, that's right. I'll put it. Yeah, I'll do a conversion.